In this lecture, we'll continue our discussion on work, and in particular, we'll look at path and point functions and exact and inexact differentials. We have seen in the previous lecture that work done during a quasi-equilibrium process depends upon the path followed by the system in going from one state to the other. For example, if you have a gas in a cylinder piston arrangement that is compressed from state 1 to state 2 through a quasi-equilibrium process, then we have seen that the work done dW on the system is given by minus PdV, and this is the differential work, and the total work is given by this equation. So the work that is done during this process is different than work that is done, let's say, in a different process where a different path is taken on this PV diagram. On the other hand, thermodynamic properties have definite values for a given state. For example, pressure and volume at state 2 have definite values, and they are independent of how one has arrived to state 2. That means the properties do not depend on the path taken by the system to attain that particular state. Therefore, what we say is that thermodynamic properties are point functions. That is, the value of thermodynamic properties does not depend upon the path. They simply depend upon the point or the state of that system at that particular point. And the differentials of the point functions are called exact differentials. For example, V, the volume over here, is a thermodynamic property. So V is a point function, and the differential dV is an exact differential. If we integrate an exact differential from one state to the other, you will get the change in that thermodynamic property, which in this case is volume. So you will get the change V2 minus V1 that depends only on the terminal states V1 and V2 and not on the path that has been taken by the system to go from state 1 to the state 2. And this is a property of a point function. For the same reason, if we have a cyclic process where the system returns back to its original state, then the change in any thermodynamic property will be zero. For example, if we look at the change of this volume dV integral over the whole cycle, and this cycle can be, let's say, on a PV diagram, is something like this. So you start from one state and you return to that state. So clearly the integral depends upon the difference between the initial and the final states, but those states are exactly same, so this integral is zero. In contrast to thermodynamic properties, work is a path function and not a point function. The differentials of path functions are called inexact differentials. For the same reason, when we denoted differential work in the previous lecture, we did not write dW, but we strike out this d with a horizontal line to denote that the differential work is an inexact differential. So exact differentials are denoted by, let's say, dV, which is the differential volume, and inexact differentials are denoted by d, which has been cut by a horizontal line, W. You will also see an alternate way of representing this, and that is delta W, and any notation is fine provided you use it consistently. So as we have seen in the previous lecture, a path function depends upon the specific path that has been taken to arrive at a particular state. And for the same reason, if you consider this process, let's say process A, where we go from state 1 to state 2, then if we calculate the total work done in this quasi-equilibrium process, then it is not equal to, or we cannot write it as difference between W2 and W1. There's nothing like W2 and W1, because such difference you can write only for thermodynamic properties or point functions. And for the same reason, we never write something like delta W, because work does not depend only on the final or terminal states, it also depends upon the path. So if you take a separate path, let's say this path B, then the value of work done would be different. So what we say is that we can use this notation that the work done during the process is W12. That means the process that takes the system from state 1 to 2. But note that there might be many different processes by which you can go from state 1 to state 2, for example, shown in this plot. So we have seen in the previous lecture that if we have a quasi-equilibrium process where we change the volume of a gas, then the differential work is given by minus P dV. In other words, I can write dV is equal to minus 1 over P dW. Note that on the left hand side, dV is an exact differential, whereas dW is an inexact differential. Exact differentials, sometimes you will also see the terminology, they are also called as perfect differential. So what we see is that this factor 1 over P, and there's a negative sign, then it converts this inexact differential into an exact differential. So factors such as 1 over P over here are called an integrating factor. So an inexact differential, when multiplied by an integrating factor, can be converted to an exact differential. But this might not be true for all inexact differentials, but if an integrating factor exists, then you can convert this inexact differential to an exact differential. And later on in the course, and particularly when we discuss the second law, we are going to see such kind of an integrating factor. Now, let us look at an example where we can analytically compute the work that is done in a process. So in this case, we'll again look at that piston cylinder arrangement where the gas is compressed, and we know that the differential work is given by minus P dV, and the total work is given by the integral over here. In this example, we'll consider a case where we know this expression of pressure as an analytical function of the volume. And one such process is called a polytropic process, in which P and V, pressure and volume, are related by this relation. PV raised to power n is a constant, where n, that is the exponent, may take positive or negative values depending upon the process. So many processes can actually be approximated by this polytropic process. Now that we know pressure as a function of volume, we can calculate work. So to this end, we'll substitute the expression of pressure from here into this equation. And this is equal to this constant times, so we have integral of v raised to power minus n. So when we integrate it, we get v of 1 minus n over 1 minus n, and the limits are the volumes in state 1 and state 2. So we get constant times v1 raised to power 1 minus n minus v2 raised to power 1 minus n over 1 minus n. And note that here W denotes the work done on the gas, which we are taking to be positive in our sign convention. And what is this constant? So if we know state 1, where it is characterized by pressure P1 and V1, and state 2 characterized by pressure P2 and volume V2, then this constant can be both P1 V1 raised to power n or P2 V2 raised to power n. So what we can do is, for the first term, we can choose this constant to be P1 V1 raised to power n. That is how we can write it. So we have P1 V1 raised to power n times V1 times 1 minus n. And for the second term, we can write the constant in terms of second state. So we get P2 V2 raised to power n times V2 times V2 raised to power 1 minus n over 1 minus n, and that simply becomes P1 V1 minus P2 V2 over 1 minus n. So that's the solution. But note that if you had n equal to 1, then this is not the formula that you would get. This is not the integral that you're going to get. In that case, for that special case, when n is equal to 1, then you would get work is equal to minus constant integral of dv by v, and that would be the natural logarithm. So minus constant log of v2 by v1, and this constant can be p1 v1 or p2 v2. Again, note that in our notation, W is the work done on the system. So if you want to find the work done by the system, so work done by the system would simply be minus W. So we have seen an example of work done during a quasi-equilibrium process where a gas is compressed by a piston in a cylinder arrangement. Similarly, we can write expressions for work in other systems undergoing quasi-equilibrium processes, and we are going to discuss some of those. In each case, you will see that the work is given by integral of product of some intensive property, let's say F, and a change in an extensive quantity, let's say dx. So you'll see that whatever may be the case, your differential work done during a quasi-equilibrium process will be of the form that you have an intensive quantity times differential of an extensive property. For example, we've already seen if you have F is equal to minus P for the compression of the gas, and X is the volume. That's why dx was dv. Similarly, we are now going to look at other systems, and in every case, for quasi-equilibrium process, your work done or the differential work would be of this particular form. So let us look at these cases. So the first case is that of a stretched wire. It could also be, let's say, an elastic band or a rubber band. So let's say that you have a wire that is fixed at one end and it is being pulled, and let's say this is the length of the wire. Then if the tension in the wire is denoted by tau, then the work done to stretch this wire or the rubber band by length dl is given by, and this is the work done on the system. So clearly you need to do work to extend the length of this wire, would be tau dl, and this is the differential work, and you can integrate between the two equilibrium states for a quasi-equilibrium process. And again, to compute this integral, you need to know tau as a function of L. And clearly, to define the state of this system, we are using two properties, that is the tension and the length of the rubber band or the stretch wire. Therefore, the tension would be a function of length only. Note that in this case, the minus sign that we saw in minus PdV work on the gas is missing. So here we have a plus sign and not a minus sign. This is because in our sign convention, the work done on the system is positive, and you need to do work to have a positive change in the length. That is, for dl positive, you need to do positive work. On the other hand, for compressing a gas, for reducing the volume, you need to do positive work on the system. That's why you will see that mostly the negative sign will always be there for a compressible system such as a gas. For all other cases, you will mostly see a positive sign in the definition of differential work. Now let's look at another example that comes to my mind, is that of a liquid film. Consider this liquid film, let's say a soap film, that is maintained on this wire frame, and all these three sides, this side, and this side of the wire frame are fixed, but this boundary is moving. By moving this boundary, we can change the area of this liquid film. Now this liquid film has surface tension, which we'll denote by sigma. And note that the units of sigma are force per unit length. Now let's say that we move this boundary so that the area of the film increases. So if I denote area by A, then this differential increase in area is denoted by dA. And if this is done slowly so that the system is in quasi-equilibrium, then the work that is done on the system to increase the area of the film by dA is sigma times dA. So again, sigma has units of force per unit length and A has unit of length squared. So you will get units of force times length, that is the unit of work. And similarly, the total work can be computed by integrating over the path. So again, in the stretched wire, we've seen the work is given by tau dl, where tau is this an intensive property and L is our extensive property. In the case of liquid film, the surface tension is intensive property and the area of the film is the extensive property. Let's look at more examples, and every time you will find that quasi-equilibrium work would be defined in terms of intensive and extensive properties. So let's look at example of electrical work. In the previous lecture, we've already seen an example where we had this battery that drives a motor, and this motor, let's say, drives a fan. So if we consider a system such as this, then we've seen that the electrical energy that flows across the system boundary can be considered as work. So consider that you have a system where you have the system at potential phi, let's say with respect to the surroundings, and differential charge dc flows into the system through a quasi-equilibrium process. Then the work done is given by this potential difference times the charge, and this is the work done on the system. That means if you have a charge, let's say a positive charge, and you want to move that positive charge into a higher potential system, then you will have to exert work on the system. Therefore, we have a plus sign over here. We do not have a negative sign. So this is an example of electric work. Again, we have this intensive property multiplied with the differential of an extensive property. Similarly, we can look at an example of a magnetic system. One example of a magnetic system is that of magnetocaloric refrigerator. So essentially, if you have a material which has these magnetic dipoles, and then you apply a magnetic field B, and these dipoles will get aligned. So that means the magnetic moment M is going to change. So the work that you need to do to change the magnetic moment by dm is given by B times dm, and this is the work for a quasi-equilibrium process where the magnetic dipole moment changes by dm due to application of magnetic field B. And such kind of work is done in magnetic systems, for example the magnetocaloric refrigerators. This is an example of a refrigerator where you don't use the vapor compression cycle. You can use magnetic fields to achieve refrigeration. Now, we've seen many examples of various systems and the definitions of the work that crosses the boundary during a quasi-equilibrium process of that systems, for example, for electrical works, magnetic work. And there could be systems where there are multiple modes of work. For example, if a system has all these processes, then the total work would be sum of all these differential works, which will be minus p dv tau dl for a stretched wire, sigma dA for a liquid film, phi dc for electrical work, and bdm for magnetic work. And you can add more terms. Again, note that each term involves intensive property multiplied by differential of an extensive property. In other words, the intensive property can be viewed as the driving force that causes change in the corresponding extensive property. Now, irrespective of the form of the work, the unit of work remains the same. And you all know that the SI unit of work is joule, which will denote by capital J. So 1 joule is equal to 1 Newton meter. And the rate, that is the time rate of doing work, is called power, and the units of power are watt, denoted by capital W. So 1 watt is equal to 1 joule per second. Previously, we have looked at forms of work done on the system in a quasi-equilibrium or reversible processes. However, work can also be done during non-equilibrium processes. Let's look at an example of such a process. So again, we consider this piston cylinder arrangement where we have this gas contained in the cylinder and we apply some force and compress this gas. We've seen that if we apply the force slowly, or that means if we take the piston slowly and compress the gas, then the process can be approximated as a quasi-equilibrium reversible process. However, let's say that if this piston is pushed into this cylinder very fast, or let's say impulsively, you suddenly push this piston at a high speed, then you will not have a quasi-equilibrium process, because then the pressure within the gas would be different at different locations. So you cannot define the state of the gas with one pressure. In fact, in this particular case, you will have a pressure wave that will propagate and then interact with these walls of the cylinder in a complex fashion. So the pressure is not going to be same throughout the gas at every point. So this is an example of a non-equilibrium process. And recall that on a PV diagram, we may plot the initial and the final equilibrium states, but we cannot define a path that the system takes, and that's why we denote it by a dotted line. That means there is no way we can calculate the area under this curve, because this is not the exact path that the system takes. In fact, we cannot define the path, so we cannot write that work is minus TdV for such kind of non-equilibrium processes. Although you would need to do work on the system, but you cannot compute in this fashion the way we have done it for quasi-equilibrium processes. Now again, I would like to reiterate that work can be identified only at the boundaries of a system. That is, work is a form of energy in transit. To understand this, let us return back to the system where this battery drives a motor and the motor is attached to a pulley. And on the pulley we have a weight that is suspended. So as the motor turns the shaft, the weight is raised. Now let's look at this case. So if we consider a system boundary such as that shown in this red colored dashed line, then our system comprises of the battery and motor. In this case, clearly the system that is enclosed by the boundary does work. In fact, the work crosses the boundary where the system boundary intersects with this shaft. And this work can be associated with the torque acting through the angular displacement. However, if we choose system boundary that is shown in this yellow color, then no work is done by the system, even though the battery is operating the motor and the motor is turning the shaft and the weight is being raised. This is because work comes into picture only at the system boundary. And you can see that for the system boundary shown in yellow color, there is no work crossing the system boundary. Therefore, we say that the system enclosed in this yellow boundary does not do work, or there's no work done on the system. Later on, we'll see that in this case, where we have the system enclosed in the yellow boundary, that raising of the weight can be identified as change in the potential energy. But this is not work, because work must cross the system boundary. Finally, let's look at an example, and you can tell me what should be the answer to this question. So consider that we have a rigid cylinder over here, which is partitioned into two chambers by this diaphragm. One chamber is filled with high pressure oxygen, and another chamber, that is over here, is also filled with oxygen but at a lower pressure. Then what we do is that we remove this diaphragm or partition, and these two gases will mix with each other. So the question is, if I consider a system that is demarcated by this system boundary shown in this yellow dashed line, that is, the system comprises of the gases in both chambers, then the question is, what is the work done on the system? And you can ignore the work that is done to remove this diaphragm, and after that diaphragm is removed, you can tell me what is the work done on the system, provided that the walls of this cylinder are rigid. So you can answer this question in the comment section below. With this, we have come to the end of the discussion of work, and we'll now discuss heat in the next lecture, and thereafter we'll be able to introduce the first law of thermodynamics.